Welcome to qnawire.
We're going to revisit the Thomson model of the atom, which existed at the turn of the century. This is often called the plum pudding model or the chocolate chip cookie dough model. The idea is quite simple, that the atom consists of a positive charge smeared uniformly throughout a sphere of radius r. It was known that atoms radiate energy, and so the question is, can we get that electron to oscillate inside the system in some way? So we're going to go through some steps. We are basically going to use the Gauss's law to determine the electric field inside the atom, the radial component. Then we are going to use that to find the force on the electron as QE. It'll be a radial force. We're going to see if that is a simple harmonic oscillator relationship or not. And if so, we are going to use the simple harmonic oscillator relationship for frequency as a square root of spring constant over mass in order to predict some things about the radiation from this atom. So that's a lot of steps, but let's kind of just write the first two down and worry about the last if we come to that conclusion, which, foreshadowing, yes, we will come to that conclusion. Okay, so using Gauss's law to find the electric field, what we want to do is draw a little Gaussian surface somewhere inside the atom at a distance little r from the center. And what we know from Gauss's law is that the electric field dotted into the normal to that Gaussian surface, the electric flux, is equal to the enclosed charge over epsilon naught. Now, usually Gauss's law is not helpful unless you don't do the integral on the left-hand side. That is, you pick a surface along which you expect the electric field to be uniform or constant, and then the integral drops out. So for a sphere, of course, it is a spherical surface, and the component that goes with that is the radial component. What you have to do with the other side, though, is to find the enclosed charge. If it's not point charges, what you'll have to do is integrate the density against the volume of the sphere. And writing down the volume element of that sphere, the density is uniform. And so we just have the volume of the sphere going out not all the way to R, big R necessarily, but to little r. So the volume of sphere is 4/3 pi r cubed, and that's little r. Okay, so solving this relationship for the radial component of the electric field, what do we get? ER is some 4 pi's cancel, a factor of r cancels, and we are left with r times rho over 3 epsilon naught. Okay, so yeah, just showing what cancels. The 4 pi cancels, and r squared goes down to r to the first power. Okay, so yes, this is exciting. So let's think about the electron. If it is sitting at the origin in the middle of the sphere, feels no force. should put a negative E for the charge. That would help. When R is equal to 0. When it grows, the force is negative E rho R over 3 epsilon naught. And that is proportional to the displacement. So there are two things to notice about this force. It is negative, meaning that it is a restoring force, that electron wants to go back to the equilibrium. Secondly, the force gets larger proportional to the displacement. And if you remember Hooke's law, working for a spring, that's exactly the characteristic you need for a Hooke's law force. Is the force of a spring is a restoring force that is proportional to the distance displaced, with a spring stiffness constant as the constant of proportionality. We have exactly this, and it is this force, if we use Newton's second law and write the force as ma, which is the second derivative of x with respect to t, gives us a differential equation with an oscillating solution. And that is the simple harmonic motion equation, differential equation. We have the same thing here, except it's a radial force. But our radial force would be m, the second derivative of the radius with respect to time squared, and that's the mass of the electron, is equal to minus E rho over 3 epsilon naught times the radius. So we can interpret all those numbers out in front of R as our effective spring constant. The E, the rho, the 3, and the epsilon naught. Okay, yes, so yes, we do have simple harmonic motion. So now on to the next step, which is to find some characteristic about an atom to produce observed radiation. And it looks to me that they've chosen a frequency associated with a red wavelength. So we can move on to the next question, which is, what is the radius of the atom to produce radiation, red radiation? With frequency 4.57 times 10 to the 14th hertz. Okay, so the idea is the electron, in oscillating back and forth, will act like a little antenna and emit radiation. Of course, what powers it is a little bit hard to understand, but let's not go there. How do you conserve energy when the electron's continuously spitting out energy? Anyway, that's not the route to go. So we know that the angular frequency of a spring, mass on a spring, is its stiffness constant divided by its mass. And that is 2 pi times the linear frequency in hertz. So we can put all this together, square it. So Ks over m is 2 pi frequency squared. And that Ks is E rho over 3 epsilon naught times the mass of the electron. And where is the radius? It is buried deep in the density. Okay. The density is the charge per unit volume, 4/3 pi r cubed. So notice I get to choose which atom. And I think it's simpler to think of one little electron oscillating back and forth. So we are going to choose a hydrogen atom. If it doesn't work for hydrogen, we're not likely to see it work for anything. Okay, so we want to take that relationship and solve it for the radius of the atom. Okay, and it's a lot of numbers that we want to crunch. 2 pi f squared is equal to e squared over 4 pi epsilon naught, mass of the electron r cubed. Yeah, let's flip that around. So r cubed, yeah, I don't know if I need to write this, except it's a lot of numbers to put in. That could potentially go wrong. But we have all those numbers. So 1 over 4 pi epsilon naught is just the electrical constant. 9 times 10 to the 9th. Yeah, newtons times meter squared over coulomb squared. E, of course, is our fundamental unit of charge for the electron and the proton. The mass of the electron, can't remember if Thomson, I don't know whether he knew the mass of the electron at the time of the plum pudding model. And the frequency was given to us. And putting all that together, I'm going to check my numbers simply because there are a lot of them with exponents galore. And we'll check one more time. And the cube of the radius winds up to be about 3 times 10 to the minus 29 cubic meters. And if we take the cube root, it does a surprisingly good estimate that our radius is approximately 3 times 10 to the minus 10 in meters. And you know, that was about the order that people suspected atoms to be from other experiments. We won't go into those other experiments, but they were basically things like depositing metals on electrodes and creating single layers and checking mass loss, things like that. So yeah, it did surprisingly well, but there are a number of things that it could not explain. One of those being, how does the electron get its energy? Why doesn't it just drop down into the center and stay there? The other thing that was a little problematic is, why doesn't the electron combine with a positive charge and become neutral? So there were a number of problems with the model that could not be quite explained. One interesting question too is, what would happen if the electron got so much energy put into it that it actually got displaced outside of the positive Q density. What if it were really ripped outside of there? Would it undergo simple harmonic motion? And of course, it would not, because your electric field, using the principle that that sphere will act like a point charge, the electric field outside does not look proportional to R. It is, of course, 1 over R squared. And so there is the wrong dependence for the force. The radial force is no longer proportional to displacement, but has this nonlinear 1 over R squared dependence. So not a Hooke's law force. Now, the electron may oscillate. There are a lot of things that approximate a simple harmonic oscillator, even though they aren't perfect. But this would not be a simple harmonic motion.